Welcome back, everyone. Today, we are continuing our deep dive into the Unified Modeling Language, or UML, specifically focusing on sequence and use case diagrams. Before we get into the notation, let's talk about the philosophy of how we use UML. First, it can be used simply as a sketch. This is an informal, highly selective, and dynamic way to communicate. In forward engineering, you might use a sketch to describe a concept before you write a single line of code. Conversely, in reverse engineering, a sketch helps you explain how an existing piece of a program actually functions. The next level is using UML as a blueprint, where the emphasis shifts toward completeness. Here, forward engineering involves creating a model that serves as a detailed specification for a programmer to follow. For reverse engineering, the model acts as a code browser. Many modern development environments support round-trip engineering, where tools allow you to move back and forth between the design and the code, keeping them in sync. At its most formal level, UML can be treated as a programming language. In this paradigm, UML models are automatically compiled into working code, often referred to as executable UML. This requires sophisticated tooling because, in this context, the model is the code. Regardless of the level, we use these models for package decomposition, class abstraction, and identifying critical dependencies within our systems. Moving beyond individual classes, we use UML for package decomposition to manage system complexity. Consider a hotel management system. We can decompose it into a service package and a financial package to isolate different areas of concern. This helps us see which high-level components contain specific sets of classes. This leads us to class abstraction. In a complex system, you often need a higher-level class diagram to show broad relationships, like a guest making a payment, while a lower-level diagram provides the technical specifics, such as showing that payment and expense are both types of transactions. Decomposition is also vital for finding dependencies between subsystems. By looking at the package we've defined, we can clearly see if the service package relies on or uses the financial package. Understanding these couplings is essential for maintaining a clean architecture. When we decide what to model, we look at three main areas. The first is the structure of the code, which involves mapping out code dependencies, components, and the level of coupling between different parts of the system. The second area is the behavior of the code, which we model through execution traces and state machine models for complex objects. Finally, we model the function of the code, which asks, what specific functions does this software provide to the end user? To model that behavior, we use sequence diagrams. These diagrams visualize individual scenarios by showing the interactions between users and the system through a sequence of messages. For example, when an order object receives a calculate price message, the diagram shows the resulting calls to order line, product, and customer objects to retrieve quantities and pricing details. Sequence diagrams are excellent for visualizing specific design choices. By mapping out the messages, you can compare different ways to implement a feature. One design might have the order object to do most of the work, while another might delegate more responsibility to the customer and product objects. We can also model object creation and deletion over time. In a database scenario, a handler might create a query command, which in turn creates a database statement. Once the results are extracted, and the objects are no longer needed, we mark their destruction with an X on their lifeline. To handle complex logic within these sequences, we use interaction frames. These frames allow us to model loops, such as iterating through every line item in an order. They also allow for alternatives, to handle if-else logic, and optional blocks that only execute under certain conditions. There are several standard operators for these frames. Beyond, alternative, optional, and loop, we use par for parallel execution, region for critical sections where only one thread can execute at a time, and neg to show an invalid or forbidden interaction. We can also use ref to refer to a sequence shown on an entirely different diagram. So when should we use sequence diagrams? They are best for comparing design options, assessing performance bottlenecks, like an object that too many messages pass through, explaining design patterns, and elaborating use cases to show exactly how the user interface should operate. Modeling a design pattern, such as the observer pattern. This pattern is crucial for managing one-to-many dependencies where you need to maintain consistency between a single subject and multiple observers. When the subject changes, it pushes updates to all its registered observers. Here we see the observer pattern represented in a sequence diagram. The diagram utilizes a par frame to show the subject sending update messages to multiple concrete observers in parallel. After receiving an update, each observer then calls getState back on the subject to synchronize its internal status. When we draw these diagrams, there are several style points to keep in mind for maximum clarity. Regard spatial layout. Use a left-to-right ordering of messages and place proactive actors on the left with reactive objects on the right. For readability, keep it as simple as possible. It is perfectly acceptable to omit obvious return values for object destructions to focus on the critical interactions. Finally, ensure consistency by keeping class names identical to your class diagrams, and ensure message routes match your established class associations. Now we pivot to use case diagrams. While the diagrams we've discussed so far focus on internal structure and logic, use cases help us bridge the gap between technical requirements and user needs. This is the heart of use case-driven design. This methodology involves using user stories. Common in agile frameworks like Scrum or Extreme Programming. To introduce UML into the software process. This approach allows us to develop domain models and use cases that are grounded in actual user requirements. As a quick refresher of UML notations, remember how these pieces fit together. Class diagrams show information structure, package diagrams show the overall architecture and component dependencies, and sequence diagrams show individual execution scenarios. Use cases, by contrast, represent the user's view, listing functions and providing a visual overview of the main system requirements. So what do users want? We begin by identifying the roles involved through user stories. These are simple statements that identify the role of the person who wants a feature and why they want it. We use UI storyboards, which are sketches illustrating how a user will perform a specific task. These storyboards show the step-by-step interactions at each stage of the process and are a staple of effective UI design. Once we have these stories, we need a way of tracking them. In an agile environment, this often involves a physical or digital board showing which stories are checked out or done, accompanied by burn-down charts to monitor the progress of the sprint. Now we'll take a look at a concrete example of an industrial use case diagram, specifically for a brokerage trading firm. First, notice the large rectangle surrounding the center of the diagram. This represents the system boundary, which clearly defines the scope of the software system versus the external entities it interacts with. Outside of this boundary, we have our actors, which are represented by stick figures. These actors define the roles that interact with our system, with the trading manager and the trader on the left, and the salesperson and external accounting system on the right. The ovals located inside that boundary are the use cases, representing the distinct set of features or functions the system provides to these actors. In the specific brokerage scenario, the functions include set limits, analyze risks, price a deal, capture a deal, update accounts, and value a deal. So if we look at our top left stick figure, the trading manager, he is our senior person who runs the entire trading desk, or he's the boss in our trading or brokerage software. And he only has one use case, set limits, because his job is not to trade every day. His job is to protect the firm or create guardrails that prevent traders from doing anything that will break that limit. Now, when we look at our trader, this is our heavy or frequent user because it's his full-time job. He sits on the screen all day executing deals, and that's why he's connected to 3 of these use cases: analyze risk, price a deal, and capture a deal. And one more actor is our salesperson. Why is there a 4th human role? It's because in real trading desks, you have 2 different kinds of people: an internal trader and a client-facing salesperson who brings the customers. They don't analyze the risks themselves. That's the trader's job. But they absolutely need to know the price before they can quote a client. Our stick figure on the far right labeled accounting system is not a person. It's an external software system. Once a deal is captured, our trading system automatically triggers update accounts to keep the firm's official books in sync. Notice the 2 includes arrows pointing to value a deal. In UML, includes means mandatory reuse. So every time you price a deal or analyze risks, the system is forced to run value a deal first. Without this crucial step, our actors literally can't know what price to quote the client or whether this deal will break any risk limits the trading manager has set. This brings us to a formal look at the relationships between use cases, specifically extends and uses. We use extends when one use case adds behavior to a base case, such as a print campaign summary extending a budget check. This is typically used to model a part of a use case that the user sees as optional system behavior or a separate subclass of logic that is only executed conditionally. On the other hand, a uses relationship, sometimes called includes, occurs when one use case explicitly invokes another. This is a critical architectural tool used to avoid describing the same flow of events several times. By putting common behavior into a use case of its own, like find campaign, you can have multiple other cases reuse that logic whenever needed. We can further refine these models by using generalizations. We first identify actor classes, where several specific actors belong to a single class. In this hierarchy, actors inherit use cases from their parent class. Some use cases might be required by every member of the class, while other, more specialized use cases are only needed by specific members, such as campaign manager, having access to features a general staff contact does not. It is also sometimes useful to identify use case classes, which allow us to define a generalization for several related use cases to simplify the overall requirement structure. The diagram is only the visual summary. For every use case, there must be a flow of events document written strictly from the actor's point of view. This document describes exactly what the system must provide to the actor when that use case is executed. Contents for this document include a clear definition of how the use case starts and ends, the normal flow of events, and separate sections for alternate and exceptional flows to handle errors or variations. You have several choices regarding the documentation style used to elaborate these descriptions. A standard English language description is the most common for general clarity. However, activity diagrams are excellent for modeling complex business processes, while collaboration diagrams are well suited for high-level design. If you need a truly detailed design that shows how internal objects interact to fulfill their requirements, sequence diagrams are the preferred choice. Now let's examine a detailed use case description for the buy a product scenario. This specifies a main success scenario consisting of 8 steps, beginning with the customer browsing the catalog and ending with the system sending a confirmation email. Below the main flow, we define extensions to handle variations. For instance, Step 3A handles a regular customer by displaying their default shipping and billing information. Step 6A details the system's response if it fails to authorize the customer's credit card, allowing the user to either re-enter their information or cancel the transaction. And lastly, you can see the buy a product scenario visualized in this simple use case diagram. Just don't mind it looking a bit rough. However, we can just even view or see the customer actor interacting with the checkout in the use case. So if we look at how the checkout is broken down into several includes relationships, such as fill in shipping info, calculate full price, and enter CC info, the diagram also explicitly shows the interaction between the system's payment logic and the external credit card company actor during the process credit card payment stage. Finally, we must consider the process of finding use cases. One effective method is to browse through existing documentation and perform a linguistic analysis. Noun phrases often indicate potential domain classes, while verb phrases represent operations and associations. Possessive phrases can help identify attributes. For each actor, you should ask a series of questions. What functions does the actor require? What specifically does the actor do? Does the actor need to read, create, destroy, or modify information? Do they need to be notified of system events or notify the system of external changes? Always consider if the actor's work could be simplified or made more efficient by adding new system functionality. That's the end of the lecture, and have a great day.